Okay, I'm going to talk about numbers, systems, and different bases, and do a little conversion between number systems, and then a little bit of arithmetic. So what I'm using here is the notes, the lecture notes. So you might want to print these out. I recommend you print these out, and then you can follow along. Now I'm going to go kind of quickly through this because I'm expecting you to read this, more than once, and read it slowly and take your time. And I don't want to waste too much time with the lecture, so I'll go kind of quickly. But look at this again at your own pace. Right. There's a little bit of section at the beginning here about a history of number systems, very briefly, and the concept of a positional number system. But the basic idea is that there's columns, and each column has a value. We've sort of settled on a base 10 number system now, which we're trained from very early age to think in, and it's important to understand that it's really completely arbitrary that we're using this base 10 system. But we've learned to multiply, add, divide, all of that in base 10. So it's really difficult to not think in base 10. So keep that in mind. All right, so in base 10, or decimal, we have the symbols 0 through 9, right? So the biggest symbol is 9, which is one less than the base. There's a total of 10 symbols. Okay, and the columns have values that are powers of the base. So 10 to the 0 is 1, 10 to the 1 is 10, 10 squared is 100, 10 cubed is 1,000. And then the symbols indicate how many of each column we have. So this means we have 2 1s, and 3 10s, and 4 100s, and 5 1000s. Okay, you can write that out with a big arithmetic expression here. 5 1000s, 4 100s, 3 10s, 2 1s. You add that all up and you end up with 5,232, which is of course what we started with. So the point of this is that it works for other bases as well. For base 10, it kind of maybe helps you understand this column value thing, 1, 10, 100, 1,000, but it's a little bit redundant for base 10, but it's useful for other bases. So let's look at other bases. So in computing, we use binary, or base 2, and it has 2 symbols, 0 and 1. The column values are powers of 2, so 2 to the 0, 2 to the 1, 2 squared, 2 cubed, or 1, 2, 4, and 8. And if you continued that, it would be, you'd keep going, 16, 32, 64, and 128. And because there's only 2 symbols, 0 and 1, 0 means we basically have that column value, and a 1 means, or rather, I'm sorry, a 1 means that we have that column value, and a 0 means that we don't. So the binary value 1010 in base 2, what's that in decimal? Basically, briefly stated, it's gonna be 10 because we have an 8. This bit means we have an 8, and this bit means we have a 2. So this is spread out a little bit more in detail, but so the binary value 1010 means that we have 1 8 and 1 2, which adds up to 10. And this expression here is probably a good level of abstraction. 1 8, 0 4s, 1 2, and 0 1s, which add up to 10. So we basically converted a binary value to a decimal value just by adding up the bits. And so the inverse of that would be subtracting bits. Like if we wanted to go from decimal to binary, instead of binary to decimal, we could just subtract the bits. So remember, the column values continue increasing. They keep increasing by powers of 2, in this case doubling. So let's say you had 42 and you want to convert that to binary. Well, the biggest value that will come out of 42 is 32. So you subtract a 32 and you end up with 10. And the biggest value that will come out of 10 is 8. and subtract, so you subtract an 8 and you get a 2. And then you can subtract a 2 and you get 0. So 0 means you're done. So we basically took out a 32, an 8, and a 2. So we need a 32-bit, an 8-bit, and a 2-bit, which would be this pattern here. Right? It would be, this is a 32, the 32 column, this is the 8 column, and this is the 2 column. Or 32 plus 8 plus 2 is 42. Okay, so that's this positional number system concept applied to base 2, where the column values are powers of 2. We can continue that. Another common, not super common, but another system that shows up in computing that's is octal. So octal has 7 digits. It's also called base 8. So the biggest value is 7. Biggest value is 7. So the base is 1 more than that, base 8. The column values are powers of 8, or 1, 8, 64, 256. And then the symbols we're using show how many of those columns we have. So the 7 here means that we have 7 256s. The 6 means we have 6 64s, 5 8s, and 42 1s. So we just add those up. So this expression right here is saying we have 7 256s, 6 64s, 5 8s, and 4 1s, which works out to be 2220 in base 10. Okay, so octal has an interesting property that each group of 3 binary digits corresponds to an octal digit. Okay, each group of 3 binary digits corresponds to an octal digit. So it's very easy to convert between octal and binary and vice versa. You just take the octal digits and expand them into 3-bit groups. So the 4, so let's convert 4506. So the 4 we just expand into 3 bits binary. So this is 100 is 4 in binary, and 101 is 5 in binary, and 000 is 0 in binary. Remember, we need 3 bits. Okay, each single octal bit gets expanded into 3 binary bits, and then the 6 becomes 110. So octal 4506 is binary, these bits, 100, 101, 000, 110. Okay, and you can go backwards very easy. You can convert binary into octal just by looking at this, at each group of 3. So you look at this group of 3, that's 6, this group of 3 is 0, this group of 3 is 5, this group of 3 is 4. Okay? So then, probably more common than octal is hexadecimal, or base 16, or sometimes we just say hex for short, although hexadecimal means 16, so it's really hexadecimal, but we say hex. Okay, the symbols are 0 through F. Okay, we were saying at the beginning, we're so used to thinking in base 10, we can't help but think in base 10. So the symbols go to F, but those letters have decimal equivalents, right? So A is 10, and B is 11, and F is 15. Okay, so we're kind of counting from 0 to 15. By counting from 0 to F, we're counting from 0 to 15. Okay, and the column values are powers of 16, or 1, 16, 256, 4096. These are powers of 16. Then you throw one of these symbols in there, like A, 7, 8, B is just an arbitrary, example. It means we have A 4096s. Remember, A is 10, so we have 10 4096s. We have 7 56s, 8 16s, and B 1s. Of course, B is 11, so we have 11 1s. So this expression here is the second row is saying we have 10A, remember A is 10, so 10 496s, 7 256s, 8 16s, and B is 11, so we have 11 1s. And that ends up being 42 891 base 10. Okay, so hex is super common because somewhere along the line in the evolution of computer hardware, we settled on groups of 4 bits. Okay, 4 bits for sizes of storage in a computer. So 4 bits is half a byte. 4 bits is also called a nibble. It's kind of cute because, you know, taking a byte is 8 bits. Half of that would be a nibble or a small byte. And because you can count to F in 4 bits, right? Right here, 1 1 1 1 base 2. That's 15 in base 10, which is F in base 16. All right, this is 15 base 10. You could check by adding up the binary digits. 8 plus 4 plus 2 plus 1 is going to be 15, which corresponds to F in base 16. So, so because of that idea of a nibble corresponding, 4-bit nibble corresponding to F, this makes a real nice system, and you only have 16 symbols to memorize or to deal with, and you can represent pretty big numbers with a very compact notation. Okay, so yeah, so that's why we have hex pretty much, is because computers are filled with binary strings, really. Everything in a computer is just a binary string, everything. But binary strings are very difficult for humans to deal with because they just kind of blend together, right? So hex turns out to be a real nice way to deal with these long binary strings that show up in computers. All right, hex has a property similar to octal in that every nibble, in this case, corresponds to 1 hexadecimal digit. Right? Every 4 bits corresponds to 1 hexadecimal digit, so it makes it very easy to convert between hexadecimal and binary. For example, what is 4FA7 hex in binary? You just expand. So 4, you turn the 4 into 4 bits binary. You turn the F into 1111 binary. You turn the A into this. A is 10, right? So in binary it's 8 and 2 gives you 10. 7 is, I had a typo in here. 7 is 0 1 1 1. And you need a leading 0 here, just like over here, because you're expanding each hexadecimal digit into a nibble. Okay, so it makes it really easy to go back and forth between binary and hex. All right? So what have we done so far? The story so far is we talked about decimal, binary, octal, and hex. So in decimal, we can count from 0 up as far as we want, but let's just limit the discussion to 4 bits. So in binary, we can count from 0 0 0 0, which is 0, to 1 1 1, which is 15. The equivalent hex would be 0 to F. The equivalent octal would be 0 to 1 7. And note where the rollovers occur. There's something called rollover, where, like here, you go to 9, and then you're out of digits, so you roll over to the next column. Right? You roll over a 1 to the tens column, so it means we have 1, 10, and 0 ones. And then we can keep counting. We have 1, 10, and 1 1, 1, 10, and 2 ones, and we can keep counting like that, and eventually it'll roll over at 19, right? What about octal? Octal, we can count up to 7, and then we're out of digits. So we roll over to the 8s column. The 1 here indicates that there's 1 8 and 0 1. This would be 8. And this indicates there's 1, 8, and 1, 1. That would be 9. Okay, like that. And then hex rolls over after F, because you're out of symbols at F. It rolls over to 1, 0. So 1, 0 hex is, it's important to say 1, 0 hex, not 10. And here say 2, 0 octal. Okay, so 1, 0 hex is 16. Because it's you have a 1 in the 16s column. And here you have, in octal, you have a 2 in the 8s column, right? So 2 8s is 16. And here I rolled over binary. I have a 1 in the 16s column. Okay, so that's the story so far. There's some patterns in here you can think about. And this is talking about nibbles and things. You guys need to be really comfortable with binary and hexadecimal. Ideally, you should have been exposed to this already, and you should be very comfortable already. In my opinion, this should be very early in computing education, really somewhere in high school. But if you didn't get this stuff yet, you need to practice it. So once again, you need to be very comfortable with binary, decimal, and hex. Octal less so, but for sure, binary, decimal, and hex. Just right now, we're going to go a little bit further than that because other bases do occur in computing, all right? So let's talk about arbitrary bases. They're not, other bases, unusual bases, you could say. So we just have a set of symbols. We can continue those. Like, why stop at F? Just keep going. Let's go to Z because we're out of the alphabet, but in theory you can keep going if you made up new symbols. But let's stop at Z. So if we did that, if we use the sequence 0 through 7, what base is that? Well, you could lay it out this way. A becomes 10. We've seen that already in hex. F is 15. And you just keep on counting. You end up with 35 for Z. So 1 more than 35 is 36. So we're talking about base 36. Just like if we were in decimal, we'd be talking, if we were in decimal, we'd be using the symbols 0 through 9, and 1 more than 9 is 10, or base 10, decimal. So our biggest symbol here is 35, so 1 more than that is 36, or base 36. It's base 36. The highest symbol has a value of 35, but there are 36 symbols. If you count these symbols, there's 36 of them. But the biggest one has the value 35. It's just a little thing that confuses people sometimes. Just like in decimal, right? There's 10 symbols, 0 through 9, that's 10 symbols. The biggest symbol has the value 9. Okay, so let's deal with base 36, this pattern here. What's RITZ? R-I-T-Z in base 36. Well, the column values are powers of 36. In other words, 36 to the 0th power, which is 1. 36 to the first power, which is 36. 36 squared is 1296. 36 cubed is this number, 46656. And the letters indicate how many of those columns we have. So R is 27, I is 18, T is 29, Z is 35. Just pulling them out of this table. So we have 27 46 656s. We have 18 1296s, 29 36s, 35 1s. That adds up to this. What is that? 1,284,119. All right. Okay, so that's the basic idea of a positional number system. We talked about decimal, binary, and then we extended this idea that you could go to any arbitrary base. So you could reduce this this base, you could cut it off here and make it base 20, right? If you just use the symbols 0 through J, it'd be base 20. If you cut it off here, it'd be base 27, right? Cut it off here, that'd be base 14. You cut it off here, what base is that? Base 4, right? You just use those symbols as base 4. Or it is base 3. We just use the symbols 0, 1, and 2, base 3. Okay, so we need an algorithm for converting to these bases. So, like I was saying, we're so used to working in base 10 in our heads that it's the only practical way for us to do these things is to. So what I'm saying is this algorithm only works from going base 10 to some other base. It doesn't go backwards because it's too confusing to go backwards, although it would theoretically be possible, but it's just too freaking hard. So this goes from base 10 to any other base, the mod div algorithm. So here's the algorithm. You take a number x, and while it's not 0, you generate a digit by modding x with the base that you're trying to go to, the base you're trying to go to. Then you change x by divvying by the base, dividing integer division by the base. You divide x by its base. So let's convert 65 base 10. It only works with base 10. Let's convert 65 base 10 to base 16. So you take 65 and you mod it by your new base 16. So remember, modulus or mod is the remainder of a division. So 16 goes into 65, 4 times, which is 64, so it leaves you 1 left over. So remember, modulus is the remainder of dividing by 16 in this case. So we have a remainder of 1. Okay, then we div 65 by 16, and we end up with 4. So this is integer division. The fraction is removed. It's truncated to integer, right? It would be 4 point something, right? But we leave the point something off. We truncate it. Okay, then we take, that's our new x, 4. Okay, then we repeat. We mod by 16. So 16 goes into 4 0 times, right? With 4 left over. And then we divide 4 by 16, which ends up with 0 point something, but we truncate 0. So that means we stop because we're at x is 0. That's our terminator for our loop. The conditional for our loop. So the answer is the green digits. It's 4, 1, base 16. And you could check because it'd be 4 times 16 plus 1 times 1, which would be 64 plus 1, which is 65 in base 10. Okay? So one more level of abstraction is that so far we've been using 0, 1, 2, 3, 4, 5 because we're so familiar with these. But you could use 1, 1, 1, 1, 1, 1. We could use Roman numerals. So 1, still got 0. The Romans didn't have 0, but you could use anything. You could use a happy face, you could use sad face, you could use a little house, you could use a star, you could use I don't know, this yin yang thing. What else? I guess I should finish. Who knows? But these are just symbols. You could even use colors. You could use red, blue, whatever. Or you could use letters. Okay, so these are just arbitrary symbols that refer to some quantity. We're just used to thinking of the quantity. When we see a 4, we think of like 4 apples or 4 bears or, 4 bananas or something. But you could use any set of symbols. So let's say we just wanted to use A, B, and C, and we wanted to generate numbers, let's call them. They're really strings that are made up of nothing but A's, B's, and C's. Okay? So the thing to realize here is that we have 3 symbols. That's going to be base 3, right? 3 symbols, A, B, and C, that's base 3. Just like in decimal, 10 symbols, 0 through 9 is base 10. So here we're dealing with 3 symbols, A, B, and C, that's going to be base 3. So let's convert 14, base 10, to base 3 using these ABC symbols. So first you have to convert just to regular base 3, just using 0, 1, 2. Just using 0, 1, 2, right? So you do that, do the mod div algorithm. You do the mod div algorithm, you end up with 1, 1, 2. So that's the answer, 1, 1, 2, in base 3. So you have to do that because we're so used to thinking about the regular numbers for counting. But anyway, do that, and then do your final mapping. Remember, A is 0, B is 1, and C is 2. So you just map. This is a. Did I do that wrong? I sure did. I did it wrong. So this should be B, B, C. Yeah. Okay, I'll fix that in the notes and repost them. All right. So we just did, what did we do? We just did a bunch of number bases and arbitrary bases and bases with weird symbols. And okay, let's talk about arithmetic. Let's say we wanted to do addition and multiplication. Let's do that well, y'all know how to add in decimal, right? I'm assuming. Let's talk about binary addition and then maybe hex and then some other arithmetic. All right. So we want to add up some numbers in binary, right? So first of all, let's look at this chart here. It turns out we're going to need to know the sum of 3 bits, all combinations of 3 bits. So you could have 3 zeros, which sums to 0, which in binary is 0, 0. And you could break the 0, 0 into 2 digits. We call the sum and the carry and the digit. So this one's the digit, and this one over here is the carry. Okay, all those bits could be 1s. You could have 3 1s, which sums to 3, which in binary is 1, 1. You can break this up into 1 and 1. And then, there's all the patterns in here, like 0, 1, and 1. That sums to 2, which is binary 1, 0. You can break the 1 up and the 0 up into a carry and a digit. Okay, so this is just a table that tells you the sum of all 3 digits. Turns out you need that because let's say we want to add 7 plus 5. Okay, so 7, we're doing A plus B, 2 numbers A and B, and we're adding them to get a number S. So A is 7 and B is 5. So A is 7. In binary, that's 0, 1, 1, 1, 7. B is 5. In binary, that's 0, 1, 0, 1. Okay, you need to add the columns. So that's where the 3rd bit comes in. So this is the carry bit. So the first carry is always 0. Okay, because it's in the first column. That's just the way it works. The first carry is always 0. So 0 plus 1 plus 1 is 0. It's this one, right? 0 plus 1 plus 1 plus 1 plus 1 is 2, or binary 1, 0. So the carry bit is 1 and the digit is 0. So carry bit is 0. Oops, misspoke. The carry bit is 1 up here in yellow, and the digit is 0. So basically, we added up this stuff in gray, 0 plus 1 plus 1, and we got a 2, and we wrote the 2 out like this. We wrote the 2 with the 1 here and the 0 here. Binary 2. That's what you do. Then you just repeat that. So 1 plus 1 plus 0 is binary 2, which you write out with the 1 up here, the 1 up here, and the 0 down here. And then 1 plus 1 plus 1 is 3, which you write out as the 1 here and the 1 there. And then 1 plus 1 plus 0 is 1. Carry the 0. Right, you could say that. 0 plus 1 plus 1 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 is 1, carry the 0. Then you bring the 0 down. And you could ignore the 0 or not. It depends on what you're doing. It depends on what happens next. But anyway, sum is 12 because you have an 8 and a 4, which sums to 12. Which is correct, right? 7 plus 5 is 12. Okay, that's binary addition. This is what happens in the adder unit in hardware. Okay, there's also a multiplier unit in hardware. So for that, we need to use, let's just use 4th grade long multiplication. Now, if it's been a while since you've done long multiplication, go call up your 4th grade teacher, and ask her how to do it. She's probably in a retirement home right now. Anyway, so go review that algorithm. We're going to just do long division, but in binary. Okay, so let's do 42 times 24, just an arbitrary example. And that should be 1008. Just checking it with I checked it with a calculator. 42 times 24 is 1008. So 42 in binary is this pattern. And you could check, right? What are the column values here? 1, 2, 4, 8, 16, and 32. So we have a 32, a 16, and a 2, which sums to 42. Here we have a 16 and an 8, which sums to 24. Okay, then what you do is you use long division. So you take this 0, and you multiply it times the whole thing on the top, and you get zeros. You take the next 0, you get a bunch more zeros. And the next 0, you get a bunch more zeros. And this 1, multiplied times the entire top, gives you the top. So the top is 10, 10, 10, which is down here, 10, 10, 10. You have to put in these leading zeros, right? That's what you do in the long division algorithm. Okay, then this 1 times the top gives you 10, 10, 10 again with 4 leading zeros. Or trailing zeros, I guess. And then you just add these up. Add up all these columns, and you get this thing, which is, it turns out it's 1008. What is that? 1, 2, 4, 8, 16, plus 32, plus 64, plus 128, plus 256, plus 512 is 1008. Okay? It's binary multiplication. Okay, it takes a long time for humans. It takes a long time in hardware as well because you got to add up all these rows. Real hardware, what is a Windows machine now? They're 64-bit, right? The registers have 64 bits. So there's going to be 64 rows. When you do a multiplication, there's going to be 64 rows. So we need to do 32 additions, plus another 16 additions, right? Plus another 8, plus 4, plus 2, plus 1. And you have to wait for each of those additions to occur. So it takes a lot of space, it takes a lot of time. All right? All right, let's do division. Okay, this is also your 4th grade division, long division algorithm. So just to remind you, because that one's a little bit harder, and it's good to see it in base 10. So this is a base 10 example. So what is 1 divided by 5? It's 0.2, exactly, right? And it terminates, that it's 0.2, done, terminates. So here's the algorithm. You take 5, you try and put it into 1, it doesn't go, right? So you look at the next digit. Now it's 5 into 10, it goes twice. 5 times 2 is 10. You subtract 10 from 10, you get 0, you're done. Okay? Let's do that in binary. So 1 divided by 5 in binary is 1 divided by 101. Okay, 101 is 5. It turns out the answer is 0011, and it does not terminate. The 0011 repeats. So here's the algorithm being executed. So we're trying to divide 5, which is 101 binary, into 1. 5 doesn't go into 1, so we put a 0 there. And then you look at the next digit. So this is now 2 you're looking at. 5 doesn't go into 2, so you put a 0. You look at one more digit. 5 doesn't go into 4, so you put a 0. You look at one more digit. Now you're looking at 8. 5 does go into 8, it goes in once. So you put a 1, and you put the 5 down here. Because 5 times 1 is 5. Then you subtract 8 minus 5, you end up with 3. Okay? Then you continue by adding trailing zeros. Because 5 doesn't go into 3. So you add a trailing 0. Actually, what I just last said, just to take that out of there. Really, you add the trailing 0 straight right away. And then 5 doesn't go into, what is this? It's 6, it does. 5 goes into 6 once. 6 minus 5 is 1. And then we're back into dividing 5 into 1, which is where we started. So if you continue this process, it would repeat. You'd end up with another 0011, 0011 forever. Okay? So you can, this and all these notes you can study on your own, at your own pace, if you need to, or play this video again, whatever works for you. But the point here is that 1/5 in base 10 terminates, but in binary, it does not. So eventually you're going to run out of space in the computer. So you can't store 1/5 exactly in a computer. So that's really important to remember. Numbers that you're used to thinking of as being, as ending, as terminating in base 10, some of them will not terminate in binary, and vice versa. Okay, but I still need to find an example of the opposite. An example of what is the opposite? The opposite is a decimal number that does not terminate in base 10, but does terminate in binary. If somebody sends me one of those, I'll stick it in these notes. Okay, let's talk about addition and other bases. So we can start with our mod div algorithm and change it a little bit, and we can add in other bases. So here's the algorithm. You add a column, and you have to add it in base 10. So I should write that in here. And then you got to convert to the base that you're dealing with. So you mod to get the digit, and you div to get the carry. And then you just repeat. So let's add beef and feed. Okay, so what is beef plus feed? So the first carry is 0, keep that in mind. So f plus d plus 0, you have to kind of write it out. It's 0 plus f plus d, and you have to convert to base 10. F is 15, and d is 13. So then now you can add those. You get 28. Then you convert back to base 16 by taking 28 and modding by 16. It gives you 12. Which 12 converts to C because we're using hexadecimal digits. And then you take the 28 and divvy by 16 and you get 1. And that's your carry. You put the yellow 1 up here and then you just continue. 1 plus E is 1 plus E plus E is 1 plus 14 plus 14, which is 29. Then you mod 29 by 16 to get the digit you need. So 16 goes into 29 once with 13 left over. 13 is really a D. And then you did by 16 to get the carry. 16 goes into 29 once. You put the 1 up here. Okay, and the D down here. And you continue like that. Okay, I think the last thing I'm going to do is some examples, okay? So you have your, this is the homework that's posted. Okay, I'm gonna do problems. Some of these are not the exact ones, but similar ones. All right. Okay, let's do from the homework. Let's convert. I'm just gonna make up one. Let's convert 2, 3, 4 base 10 to binary. So you can use the mod div algorithm. So it would be 2, 3, 4 mod 2. It's going to be this goes in a bunch of times the remainder of 0, right? And then 2, 3, 4 div 2 is what is that? What is that? It's going to be 117. Okay, that was loop 1, and this is a digit. There's no 1s, is what that means. So then you take 117 and you div by 2, and you get a 1 because this is an odd number basically. This 2 goes in here, I don't know, a bunch of times, but we get into a 1 left over. And then you take 117 and divide by 2 and you get 50 plus 58, right? This would be 116.5. So this is another digit. Then you take 58 and you divide by 2 and you get another 0, and then you divide that by 2 and you get 25, 29, and 29, 2 is 1, 29 div 2 is 14, right? And 29 div mod 2 is it's 14. 14 is going to be 0, and then 14 div 2 is 7, and then 7 2 is 1, and 7 Sorry about the typos here. It's 3, right? Then 3 modulo 2 is 1, and 3 div 2 is 1. And 1 modulo 2 is 1, and 1 div 2 is 0, and so we stop. And this is our answer, these digits. So the answer is 1, 1, 1, 0, 1, 0, 1, 0. Base 2. And you can put a caret here just to break it up into nibbles. But you can check it. So to check, let's see, so we 1, 2, 4, 8, 16, 32, 64, 128. So the check, I'm going to put it over here, so it's 128 plus 64 plus 32 plus 8 plus 2, and that should add up to 234 if I did it right. 16, 22, 4, 16, 4, 6, 7, 8. That's 24, so 13, 234, that's 10. Okay, let's do another example. Let's do let's do 52 base 8. So it's octal to let's do that. Let's go to base 7. Okay, so you have to go via base 10 because otherwise it's just too hard. So 52 base 8. What is that in decimal? It's going to be 5 times 8 to the 1 plus 5 times 8 to the 0. Basically, there's 2 1s. This is the 1s column. This is the 8s column. Right? So it's going to be it's 40, right? 40 plus 5 is 45. 45 base 10. No, it's this is a 2. It's 42. I didn't plan that. Okay, now we have 42. We can go to base. Then we use mod div. We can go to base 7. So 42 mod 7 is going to be it's going to be 6, right? Because 7 times 5 is 35. 78, 40, 41, 42. That's 0. Right? So 42 divided by 7 is 6, right? You guys got to check me on my arithmetic. And then 6 mod 7 is 0. I'm messing up here. Yeah, I confused myself. This is a 2, by the way, so it should be a 6. Because 7 goes into 6 0 times with the remainder of 6. And 6 divided by 7 is 0, so we stop. So the answer is 6, 0. So the answer is 6, 0 base 7. And then you can check because column values are it's 7 to the 0, 7 to the 1, 7 squared, or 1, 7, 49. So so a 6 and a 0 means that we have 6 times 7 plus 0 times 1, which is 42 base 10. 42 base 10. This is the answer to this. Yeah, anyway, so you have to start with 52 base 8. You have to go to base 10, and then you can use the mod div to go back to base 7, and then check that you got the base 10. Yeah, it's confusing because you have to. It's hard for us to think in base 8, and I got myself confused. But anyway, you have to go from base 8 to base 10, and then back out. Okay, let's do another one. So example, let's do an addition in a weird base. So let's add 43 base 5 plus 21 base 5. So 43 plus 21. So this is going to be, it carries 0. It's going to be 3 plus 1 is 4, and 4 plus 2 is 6. But if it's base 5, the digits are going to be 0 through 4. So this is too big. So you got to do the mod div on here. So 6 mod 5. It goes in. 5 goes into 6 once with a remainder of 1, and 6 div 5 is 1. So this really becomes this becomes 1 with a carry of 1, which would make sense because you're going over to the next column, which is 5, and then there's 5 times this column plus 1, and then you can bring the 1 in. So it should be 114 base 5. And I guess you could check these. You'd have to go to decimal for this, and then go to decimal for this, add those, and then go to decimal for this and add that. And, so that's enough, I think. I think you guys will be okay on this stuff. Yeah, so you can watch this video over again if you need to, and study this stuff, read all of this stuff, okay? And get that first homework done, and this thing, and I'll see you next time.